In this lecture, we are going to discuss the chapter 5, which is light. Light is another kind of wave, like a sound. We are going to study the phenomena associated with light. Also, we are going to discuss the nature of light, if light is a wave or is a particle. Also, please complete the index refraction lab and the homework number 6. If it's possible, start working on homework number 7. There are two different kinds of source of light. The objects can be luminous or can be incandescent. An object is luminous when produce its light, for example, the sun or the candle, or the object is incandescent when visible light is given off as a result of high temperature. One example is the incandescent light bulb. The light waves are also called electromagnetic waves because it consists of electric and magnetic field. The electromagnetic wave is a model that is used to explain the nature of the light. And let's see what is the electromagnetic model. This model was proposed by James Maxwell in 1860s, and this model describes a relationship between the electricity, the magnetism, and the light. The electromagnetic wave consists of the electric field, which is here in the picture, the blue one, the magnetic field, and one thing is this: the electric field and magnetic fields, they are always perpendicular each other. Another important feature of the electromagnetic wave is they can travel in the empty space. They can travel in the vacuum. And remember, the mechanical waves requires a medium to travel. But in case of the electromagnetic waves, they can travel in the empty space without any medium. Then let's now we describe what is the electromagnetic spectrum. The electromagnetic spectrum consists of different wave at different frequencies, and because it has different frequencies, different wavelengths also. These wavelengths can be radio, can be microwaves, can be milliliters waves, can be infrared light, can be visible light, ultraviolet light, X-ray, and gamma. One important thing is, remember, all these waves we had here belong to the electromagnetic spectrum. And all these waves belong to the electromagnetic spectrum, travel at the speed of the light in vacuum. Then the speed of any of these waves is the speed of the light, means it's 3.00 10 to the power 8 meters per second. Because all these are considered as a waves, yes, all these lists we had here are waves, then we can describe using the equation we use for describe the sound wave. But in this case, remember, the equation we use, the velocity equals to the wavelength times the frequency of the wave. But in this case, for this set of waves, yes, for all this one, the velocity in the empty space or in a vacuum equal to the speed of the light. Then the letter we use to represent the speed of the light is c. And this is why here we replace the v, the velocity or the speed, by c, and equals to the wavelength of the wave times the frequency, is the frequency of the wave. And this is why for any of the waves belong to the electromagnetic spectrum, we can use this equation to solve any of the problems. And the speed in empty space or in air also is the same value. The speed of the light is 3.0010 to the power 8 meters per second. One important thing is, or another important thing of the electromagnetic spectrum is the only part that is visible for us is the visible spectrum. Yes, is the colors red, orange, yellow, green, blue, and violet. But you can see most of the part of the electromagnetic spectrum are invisible for us. Yes, we cannot detect these waves. We cannot detect these waves also. Here I want to, because all these are waves, then we can describe these waves in terms of the speed, of the wavelength, yes, the wavelength, and the frequency. Then one thing is the radio signals always had the larger wavelength, and the gamma rays is the small wavelength. Remember, if we just rewrite this equation like lambda equals to the speed of the light, we divide by frequency on both sides, and we can just make the line test, then we can see the wavelength and the frequency, they are inversely proportional. If the wavelength, if the frequency increases, the wavelength decreases. Yes. Then what happens, because they are inverse, then the wavelength in case of the radio signal are large. Yes, it's large wavelength. The distance between two crests, yes, are really large value. Yes, here we have 10 to the power 3 means 1,000 meters, being 1 kilometer. Yes, is the wavelength, the distance between two crests. Yes, in case of the radio. But in case of the gamma, yes, is really small value. Yes, it's 10 to the power minus 11 meters. It's really a small value. Yes, the distance between the two crests are small value. Again, because this relation between the wavelength and frequency is inverse, and because we had here large wavelength, the frequency is small. Yes, but here, because we had short wavelength, the frequencies are really high. It's 10 to the power 20. Then you can see the frequency increase in this direction. Yes, the frequency increase in this direction, and this is the wavelength increases in the opposite direction, because they are inversely related. One more thing I want to notice here is this is the only part, yes, the visible light is the only part of the spectrum we can detect. And these are the colors. They correspond to the visible light, to the colors. And here I wrote here the frequency. Here is the wavelength in nanometers. Remember the nanometers. This corresponds to 10 to the power minus 9 meters. Nano is the prefix, means 10 to the power minus 9. Or we can write this one like 7.5 10 to the power minus 7 meters. It's the same thing. Yes, we move two places. And these are really small wavelength also. But one thing, if the frequency, what we can see is we can detect only the waves that the frequency is 10 to the power 14. Yes, 10 to the power 14. Then always the colors, when you had to calculate the frequency of the colors, you will see the frequency should be equal to some number, yes, some number between 1 and 10 multiplied by 10 to the power 14. This is the only frequency we can detect. Yes, it's 10 to the power 14, which correspond to the frequency of the colors. Another concept I want to discuss here is the black body radiation. Remember, when any object or any body at temperature higher than 0 Kelvin emits some radiation. It can emit some radiation, it's giving off some radiation. That radiation is electromagnetic radiation and is called black body radiation. And any body or any object at temperature greater than 0 Kelvin will emit some radiation. That radiation is called black body radiation. For example, our temperature is about 310 kelvins, which is 98 Fahrenheit, and all the humans or animals emit infrared radiation. This temperature corresponds, and if we calculate the wavelength, correspond to 10 micrometers, and this 10 micrometers correspond to the wavelength for infrared wave. Then here now we want to discuss some properties of light. We want to describe some phenomena associated with light. Then we can see there are two different. We already say there are two different kind of objects. One is the luminous when emit light, and the other are the non-luminous which reflect the light. One typical example is the sun is luminous and the moon is non-luminous. Yes. Another characteristic of the light is we cannot see the path of the light itself. Yes, but what happens if there is dust? So if there is dust, then we can see the ray of the light, and what we can see is they move in a straight line. Yes, then this is why the rays travels in straight line, like we can see clearly in this picture. That happen is that the light will travel in a straight line until this interact with some matter. Now, what happened with the light interact with some matter? Yes? Then, what is going to happen? What is going to happen when the light interact with some matter? Depend on three aspects, three different things. Yes. Then, when the light interact with some matter, like for example, we had this block here, this cube here, then depend on these three things. One, the smoothness of the surface. The nature of the material is what kind of material we had. What kind of material interact with the light. And the angle that the light strikes the surface. Yes, this the angle. And we will discuss now we will discuss each of these aspects in the next slides. Then, when the light interacts with matter, what happens is depend on the smoothness of the surface. What happens if the surface is perfectly smooth, like in this case? Then we can see here is we will see perfect reflection, yes, perfect reflection, organized reflection, and this is called specular reflection. But what happens if the surface is not smooth? Then is all the rays are scattered, yes, like we had here, in many directions, in random direction. In this case, we call this is diffuse reflection. Then if the light interact with the smooth surface, we had specular reflection. But if the surface is not smooth, then we will have diffuse reflection. Yes. The light is scattered in many directions. The second thing, then when the light interacts with matter, also what is going to happen depends on the nature of material. And what happens if the material is transparent? If the material is transparent, all light passes through. Yes, like we had glass, yes, like this one, then the light passes through. But if the object is translucent, then what is going to happen? Sunlight passes through. Yes, sunlight passes, sunlight is not passed. But what happens is opaque. If the material is opaque, then no light passes through. Yes. Then this is happening. The other thing is what happens is depend on the nature of the material. The third aspect we need to consider when the light interact with the matter is the angle that the light strikes the surface. Then if the ray strikes the surface at some angle, like in this case, most of the light will be reflected. Yes, most of the light is reflected. But if the ray is vertical, like in this direction, what happens is most of the light will be absorbed by the material. And if we had here transparent material, then most of the light will be transmit to the transparent material. If the ray is in this direction, is vertical ray. One more thing I want to add here is most of the objects we can see are because the light is reflected in all directions. Then in that case we had diffuse reflection. Yeah. We had diffuse reflection. Then in other words is the objects that are visible for us is due to the diffuse reflection. Yes. Then now I want to focus in the phenomena associated with the light. Remember we discussed the phenomena associated with the sound. Yes, some phenomena we associate with the sound. Then we want to discuss the similar phenomena, but in this case associated with the light. And the first one we want to discuss is reflection. And remember, we say we can identify, we can remember that the reflection as bounces off. Yes, this is happening. The wave interact with the matter and then bounces off. Yes, this is the same happen with the light. With the light is the incoming light, yes, is interact with the matter, yes, with the surface, and then that light is outcoming. Then the incoming light is called the incident ray, and outcoming light is called the reflected ray. Then to study this, we want to add one more parameter to this phenomenon is the normal. And the normal line, which is the green one, is imaginary line that is perpendicular to the surface. Then we had incident ray, yes, is the incoming light. We had the reflected ray, is the outcoming light, and we had the normal. Normal is the imaginary line that is always perpendicular to the surface. And why we need to define the normal? Because we will define the two important angles in terms of the norm using the normal line. Then two more parameters we will use to define the reflection in light is the incident angle and the reflection angle. The incidence angle is the angle we measure between the normal and the incident rate. Yes, is this one. Remember, is we had to measure always from the normal line. And the other angle is the reflection angle, and this angle is measured between the reflected ray and the normal, is this angle. What happened in the reflection of light, these two angles are the same. This is the real experiment, and we can see how the incident angle equals to the reflection angle. This particular experiment is about 15 degrees. And this is called the law of reflection. And the law of reflection states that the angle of incidence equals to the angle of reflection. Then remember, reflection is bounces off, yes, and in case of light, in the reflection, the angle of incidence equals to the angles of reflection. The next thing we want to define is the refraction. And remember, we say refraction, we will associate that with the bending. And the refraction occurs when the wave, in this case the light, travels from one medium to another medium. Yes. In this case, the medium is the air, yes, and in this example, yes, this is real experiment, real picture, is probably should be glass. Yes, we have glass here. Then the light is traveled from air to pass through glass. In this case, we had air and water, and here we had also air and water. And what happened with the light or the wave pass from one medium to another medium is the ray or the wave is bending. Yes, and this happened because the wave change, the speed of the wave change. In this case, that happened because the speed of the light changed. The maximum speed of the light is the value in vacuum or in air, which are really similar, is 3.00 10 to the power 8. In any other material, the speed of the light is less than 3 10 to the power 8 meters per second. Then these are real examples, and here we can see how the light is the speed of the light is changes, how the wave is bending, because we can see the difference. Yes, this is you can see the effect that produced that phenomenon. Yes, we can see something like that. And this effect is because of the change in the speed of the light from one material to another. And here we want to also to describe the what happened when the ray passed from one medium to another medium in terms of the angles we can measure from the normal line. Yes, and in this case we had the incident ray. Yes, we had here air. We had, in this case, is water. Yes, in this case we had water. That what happened is, this is the incident ray. Yes, here is interact with the water, because the ray changed the medium. Yes, from air to water, the line is bending. Then we can describe this phenomenon in terms of the incident ray and refracted ray. Yes, refracted ray. And now we will use the normal line to define these angles. Then the normal line, remember, is the line that is perpendicular to the surface. It's imaginary line. Yes, we had to draw this line. Then the angle from the normal line to the incident ray corresponds to the incident angle. And the angle from the normal line to the refracted ray is the ray we can see in the other material, is called the refraction angle. Then here, this is a real picture, and this is happening with the light passed through glass. Here we can see this is the incident angle, this is the refracted angle. And again, this happened because the speed of the light changed. For example, in air, the speed of the light is about 3.00 10 to the power 8, but in water is about 1.23 10 to the power 8. In this case, the air is about, in air is 3.00 10 to the power 8 meters per second, but in glass is 2.5 10 to the power 8 meters per second. If the ray of the light is perpendicular to the normal line, yes, if the ray is here, yes, is here, that what happened is it's not possible to see any refraction, yes, any refraction. And there is one quantity that is defined in terms of the incident angle and the refraction angle. And this is called the index of refraction. Then what is the index of refraction? How we can define the index of refraction is the ratio of the speed of the light in vacuum to the speed of the light in a material. For example, if we want to calculate the index of refraction of glass, yes, and we need to know what is the speed of the light in vacuum, and we need to know what is the speed of the light in glass. Yes. When we divide these two values, we had 1.50. The same is for diamond. To calculate the index of refraction of diamond, we need to divide the speed of the light in vacuum. We know that is this value, 3 10 to the power 8, and the speed of the light in diamond. And when we divide these two quantities, we can calculate the index of refraction of glass. Then for the speed of the light in vacuum, we will assume always this value, 3 10 to the power 8. Another thing is the index of refraction is a physical property of the material. Is we can identify that material if we know the index of refraction. One more thing here is you can see there is no unix for index of refraction. Yes, and the reason is because it's the quotient between two speeds. Yes, then in this case, let me write here. Yes, what happened with the unix? We had C is the speed of the light, and the units will be meters per second. Here is the speed of the light in that particular material. Yes, it's also meters per second. And the units cancel out. And this is why there is no units for index of refraction. Yes, this is why there is no units for index of refraction. This is how we can correlate the index of refraction with the incident angle and with the refraction angle. And this law that correlate the index of refraction of the two materials and the angles of incident, and the incidence angle and the refraction angle is called the Snell's law. And what the Snell's law say is the ratio. Yes, let's explain first the picture we had here. Then what happened is the light. This is the rate and the rate of light we had here. Yes, this is the incident light. This is the refracted light. Then is bending because the second medium is water. Then let's see the index of refraction of air, which is always 1. I forgot to mention that part. Let's see if here you see the index of refraction of air is about 1, and I forgot to mention that before. Is almost 1 because the speed of the light in vacuum, yes, and the speed of the light in air is almost the same. Yes, it's 1.0029. It's really are almost the same value. Yes, are almost the same value. And this is why we can assume these two are almost the same. Yes, are almost the same. This is why also we can assume the index of refraction of air equals to 1. Then this is why we had here N1 equals to 1. The second is the index. The second medium is water, and the index of refraction of water is 1.33. This is just example. This is that to indicate, to give some idea of values of index of refraction. And we had here is the angle of incidence, which is the angle between the normal line and the incident ray. And here we have the angle of refraction, which is the angle between the normal line and refracted ray. Yes, it's this. Then what the Snell's law say is the ratio between the medium 2 to the medium 1. Yes, medium 2 to the index of refraction of the medium 2 to the medium 1. See, this is this equals to the sine. Sine is just a trigonometric function, and the way we can calculate that is just you just type the number 25 and then you press sine. Yes, this is we are going to do in this course. Then this is just a trigonometric function, and we can calculate using the calculator. Yes, is the sine of the incident angle divided by the sine of the refracted angle. Then this is the Snell's law, and this correlates the index of refraction of the mediums and the incident and refracted angle. Then in this particular case, let's see what happens if the first medium is air. Yes, this value equals to 1. Then N1 equals to 1. Remember, N2 divided by 1 equals to N2. In the same way, 5 divided by 1 is 5. Yes, or 3 divided by 1 is 3. Then N2, or the index of refraction in the second medium divided by 1 equals to N2. Then if we conduct this experiment and the first medium is air, this law we can rewrite this law at this one. We can simplify the expression. Yes, and this is what you are going to do in the lab. Yes, lab. Another thing is if we can calculate the index of refraction from the second media, yes, from in this case from water. Yes, if we know this, we know in this case this value, but in our case we had to calculate that value. If we know this one, yes, if we know this one, then we can calculate the speed of the light, in this case in water, just if we solve this equation. Yes, if we solve this equation, then we can calculate, because we know C is 3 10 to the power 8. We know this value because we can calculate the value using this relation. Then we can calculate the velocity in the velocity of the light in that medium. Yes, in that medium. Now we want here to calculate what is the speed of the light in diamond. If we know the index of refraction of diamond is 2.42, and let's do that. Yes, this is I was mentioned here. Yes, in this part, and how we can calculate the speed of the light in that particular medium if we know the index of refraction and if we know the speed of the light in vacuum. And we know the speed of the light, the C value, the speed of the light in vacuum equals to 3.00 10 to the power 8 meters per second. We know the M value, the index of refraction, and we can now solve for the velocity. What velocity? The speed or the velocity of the light in diamond. And let's write here. Then we have this equation. And we need to solve for this variable, as we need to solve for the speed. Then we multiply by the speed on both sides. Let's cancel out. And then we need to solve for the speed. We divide by the index of refraction. And this is the equation we want. And the velocity or the speed of the light in diamond equals to the speed of the light in vacuum divided by the index of refraction, the index of refraction of diamond. No units for index of refraction, yes, no units. And if we divide these two values, then we can divide 3 divided by 2.42 will be 1.24 10 to the power 8 meters per second. Then this is the speed of the light of a diamond. Yes. Then one more thing, always the speed of the light in any material will be less than 3 10 to the power 8, because the maximum speed of the light is 3 10 to the power 8 meters per second. Then always will be less than 3. Yes, 3 10 to the power 8. Always the speed of the light is always huge value. Then always will be multiplied by some number multiplied by 10 to the power 8. Because the speed of the light is always a huge number. And if your result is 1.5 without any power of 10, then you know something is wrong, because it's always the speed of the light is a huge value. Then we defined before the electromagnetic spectrum is a set of waves, yes, with different wavelength and different frequencies. But one important thing is all these waves, yes, from radio signals to from radio waves to gamma waves, all these waves travel at the speed of the light. Yes, all these travel at the speed of the light. Then in vacuum, the speed of the light is 3 × 10⁸. Because they are waves, yes, then always, if because they are waves, they have some speed, and also there is a wavelength and frequency that is associated with these waves. Yes, and this is why we can use this equation to describe light waves. Because the visible spectrum is part of the electromagnetic spectrum, because the visible light is part of the electromagnetic spectrum, then all the visible light travel at the speed of the light. Then the speed of the visible light travels at 3 × 10⁸ meters per second. What happened is in 1672, Newton found that white light is a mixture of all these colors. Yes, this is the mixture of 6 independent colors, which are red, orange, yellow, green, blue, and violet. Then all these colors are part of the electromagnetic spectrum. Then we can consider, yes, all these colors as waves. Then all these waves travel to the speed of the light, 3 × 10⁸. And if any problem involved, we want to calculate the frequency of the red wave, yes, or the yellow wave, then we can assume the speed equals to 3 × 10⁸ meters per second. Yes, if that light is traveled in empty space or in air. One more thing I want to say here is this is the range of wavelength we can detect. Yes, it's 400 nanometers, which correspond to the blue, violet, this region, and 800 nanometers, which correspond to the red light. Then let's do some problem. Then the colors of the spectrum can be measured in units of wavelength, frequency, or energy, because now we know colors correspond to waves, yes, and we can identify waves in terms of the wavelength, of the frequency, and we will see later the energy, how we can describe the energy of the waves. We can detect, yes, all the colors. This is the only part of the electromagnetic spectrum we can detect. But the human eye is most sensitive to light with a wavelength of 5.6 × 10⁻⁷. And we say, yes, this is the one, 5.6, and this is the wavelength, 10⁻⁷ meters. Yes. We say before, I don't want to confuse you, but just remember this is the same thing. Yes, 560 nanometers. But in our case, because the speed of the light is meters per second, this is the unit we want. Yes, in meters, this is the unit we want, because we want consistent units. And we want to calculate with the frequency. And this is the frequency. This is the visible light, because correspond to this wavelength correspond to yellow green color, then it's visible. Remember, we say for visible light the frequency will be always 10 to the power 14. Then we expected in the answer some number here, yes, and here times 10 to the power 14. It will write the number in scientific notation. And let's calculate this. Let's calculate these values. And let's first solve for frequency, because this is we want to calculate the frequency. And let's write here equation. We want to solve for the frequency, then we need to divide by the wavelength on both sides. And let me write this one like that. This frequency, the speed of the light divided by the wavelength. And the speed of the light, we know this value is 3.00 10 to the power 8 meters per second divided by wavelength. And we had consistent units, then no problem. 10 to the power minus 7 meters. And let's see, meters cancel out with meters. And what we had on top is 1 over second, yes? And this is the units for frequency, and units are correct. Then now let's divide 3 divided by 5.6, and let's keep 3 significant digits. We had 0.536, 10 to the power. Then remember, for the power is the power of the denominator minus the power born. Then we had 8 minus 7. And here finally is, here we had addition, yes? Because negative times negative is positive. And finally here we had this 0.536 10 to the power 15. 1 second is, we can write like hertz. Now, if we want to write this one in scientific notation, then we can move, because we need this number between 1 and 10, yes? Then we move this one. We move to the right, then we had to subtract, yes? Move to the right, then we had here 5 point, we subtract here. Then will be 5.36. We subtract 1 because we moved 1 decimal place. Then we had 10 to the power 14 hertz, as we expected, yes? 14 should be the frequency of the visible light. Remember, always the frequency of the visible light in hertz is some number 10 to the power 14. And this is the frequency. This is the frequency of the yellow-green color, yes? Then what happened is, in 1600, the nature of light became a topic of debate. Why? Because Isaac Newton, he believed the nature of the light was a particles, means if we can explain the light, if we can assume the light are particles. And the main thing he says is because the light travel in a straight line, and also because we can explain the motion of the light using the law of motion. Then, but in the other side is Christian Huygens. Then he believed the light, the behavior of the light, they can explain the light, the behavior of the light, is if they explain the light as a wave. Then he believed the light is no string particles of there is no a string of particles, rather a longitudinal wave. Yes. Then this was the debate between these two different ideas about the nature of the light. during the 1700s, the Newton's theory was favored, but what happened is in the 1800s was more and more experimental evidence that can be explained only if they consider the light as a wave. Yes. Then now let's study what was that experimental evidence that can be explained only if the light is a wave. One of the phenomena can be now explained if we consider the light as a particle is a diffraction. And remember we defined diffraction before, when the wave can be passed around the edges and of obstacles and pass through the small openings. Then the diffraction of light occurs when the light wave passed by a corner, yes, can go around the obstacles or through the opening or slips that can be the size of the opening can be larger compared with the wavelength of the light, or can be even smaller than the wavelength of the light. Yes, but the light can pass through that slit. Yes. Then what happened is, if we had the big gap, yes, the large opening, then we see a small diffraction effect. But if this is narrow gap, yes, we can see large diffraction effect. But what happens is the light, the wave of the wavelength of the light can be even smaller. Yes, sorry, the opening, the slit can be small than the wavelength of the light. Yes, can be small, and the light can pass through this one. Yes, can pass through this one. Then what happens is this phenomenon can be only explained only if we consider the light as a wave. Yes, even if we had some opening like that. Yes, let's try to right here. And this is the opening, but the wavelength is larger than that opening. But even though the light can pass through this one, yes, pass through this one. It's just with this I want to explain, even if this is larger than the opening, the wavelength, the light can pass through this one. And this is not possible if we consider the light as a particle. It's just if you had some particle can be, for example, a ball. Yes, if you have this ball, but you had this opening, you cannot pass this ball through this opening. Yes, and this is why we can explain this phenomenon only if we consider the light as a wave, like in case of like a sound. Yes, like the same case of the sound. Yes, the sound can be diffracted. The other phenomenon can be explained only if we consider the light as a wave is interference, because interference occurs only in case of the waves. And this was this experiment was conducted by Thomas Young, and what he did is he conducted the double slit experiment. Then he passed light through one slip. Then the same light passed through two slips, and what he observed the interference pattern. Yes, here we can see some bright lines and some dark lines. Then bright line correspond to the constructed interference we discussed in the last presentation, and destructed interference. Then this is a real picture of the interference pattern. We can see here the bright lines and the dark lines. Then this phenomenon only occurred for waves. Then this is another clear evidence at this point. Yes, this was in 80s, was in the 80s, 100. There was another evidence that the light that phenomenon can be explained only if we consider the light as a wave. Then at this point, all the scientists were agreeing that light must be waves. Yes. But there is one more thing. Another phenomenon associated with the waves is the polarization. And in this picture, we are represent the unpolarized light. Unpolarized light is in which the waves can vibrate in all directions. Yes, the light can vibrate in all directions. But in polarized, when the light is polarized, that vibrate only in one direction. Yes. And if we had, for example, vertical polarized, like in this case, even if we cannot see that, yes, we cannot distinguish that. But in this case, we had unpolarized light. Then when the light passes through this one, the light can vibrate only in this direction. We cannot distinguish that, yes, when we see the light, but this is happening. Another thing is if we had unpolarized light and the light passed first through the vertical polarized, and then we had another horizontal polarized, is we cannot see the light are polarized, but what we can see is if we had cross polarizers, what we can see is we don't see light here because this is vibrate in vertical direction and this allow pass only the light is vibrating in horizontal direction. But because of the light is vibrating in horizontal, cannot pass through this one. And this is, what is going to happen is we cannot see the light here. And this we can see in this example here. This is when if we had just horizontal polarizer, we can see through this one. Yes, we can see there is something blue. There is something blue there. When we see through the vertical polarizer, we can see there is something blue there also. But what happens when we cross the polarizers is we cannot see anything through there. Yes, this is why, because the light cannot pass through this one. What is happening is this. This is what happening in this case. This is why we cannot see light on the other side. Yes, it's happening here. And what happens is when we allow the light polarize only in one direction, then is we can see the things more clearly. As in this picture, we had something without a polarized lens, and here we had with polarized lens. Yes, we can see more details in this case. Then usually the glass we use, the glass we use that are polarized, always they block the vertical, the horizontal light, allowed to pass always the vertical line, because our eyes are more sensitive to the vertical light. And at this point, we can explain the diffraction, the interference, and the polarization phenomena if we consider the light as a wave. However, we cannot explain these phenomena, these three phenomena, if we consider the light as a particle. Then, by the end of the 1800s, most of the scientists, they assumed that the light was an electromagnetic wave, and that wave can travel in the empty space. But what happened is at the beginning of the 1800s, there was another phenomenon that cannot be explained if they consider the light as a wave. Then that phenomenon is related with the light when the light is absorbed or emitted from the matter. Then one of the phenomena cannot be explained if the light is considered as a wave was the photoelectric effect. Then what is the photoelectric effect? Then let's explain first this picture. If the incoming light beam give enough energy to this metal, then what happens is if the electrons they had enough energy, then if the electrons they get enough energy, then the electrons can escape from the mirror. Then what happens is this light, yes, as a wave. This is as energy. Remember, wave is an energy. Then if this wave give enough energy to this metal and the electrons gain enough energy, then there at some point the electrons can escape from the material. And using using this fact, the Max Planck, he conducted this experiment. What he has here one positive and negative plate, and what happened, we irradiate the negative plate with different kind of light. When they say different kind of light, is different colors of light. Then what happens if the electrons they gain enough energy, then the electrons can escape. Because this is a positive plate, then this positive plate attract the electrons which has negative charge. When these electrons move or they was attracted by the positive plate, then they generate a current, and they were able to measure the current passed through this circuit. Then what they did in the experiment, they measured the energy and the number of the electrons. They measured the energy of the electrons and the number of electrons. That variables were measured when the intensity of the light was low or high, also at different frequencies. When we say different frequencies, then they use different colors of light. Yes, different colors of light. Then what they did is they measured the energy of the electrons, the number of the electrons for low intensity light, high intensity light, and different frequencies of light, means different color. And let's see what was the results. One thing is they observe when they irradiate the metal with the red light, was no emission, no current in the circuit. Yes, but when they irradiate the metal with the green light or the blue light, they had some emission. Then they were able to measure some current in the circuit, and this was the results. Low intensity light ejects fewer electrons. High intensity light ejects many electrons. But the interesting result was the following: all electrons have the same kinetic energy. Yes, all electrons have the same kinetic energy. Then when they irradiate with, for example, with green light, low intensity green light, they observe fewer electrons. When they irradiate with high intensity green light, many electrons. But what happened was all the electrons have the same kinetic energy. Then this was things they cannot explain if the if they consider the light as a wave. Why? Remember, the intensity is the power per square unit. Yes, this is the intensity. Remember, the power is the energy, the ratio between energy and time. Yes, is the energy per time. Then if we combine these two equations, we will have the intensity is the energy per unit time per area. Yes, per area. What we can see here is the intensity is direct proportionally to the energy. More intensity, more energy. But what happened is here they have more intensity, same energy. Yes. Then this is happening in case of the sounds. More intensity, more energy. Yes. Loud. Remember, in the sound, intensity is related to how the loudness of the sound. More intensity, more loudness. But what happened here is low intensity, high intensity, same kinetic energy. Then say, we cannot explain this one if we consider the light was a wave. Then the kinetic energy is independent of the intensity. Yes, was not like sound. Then it's not like a wave. But what they observe is for different colors, the kinetic energy is different. Then we measure the kinetic energy for green, they got one result. When they measured the kinetic energy for blue light, they got the different result. Then the kinetic energy of the light, yes, depend on the frequency, means depend on the color of the light. Then wave theory cannot explain this light behavior. Then in 1800, Max Planck, who was the scientist that conducted the photoelectric effect, he proposed that the only way he can explain the result in his experiment is they consider the light as vibrating molecules that emit light only if they have discrete amount of energy. Then that discrete amount of energy they call quantas. Is only some particular value of energy is allowed. Yes. But the scientists who explained this phenomena using a mathematical relation was Albert Einstein. Then he applied the quantum concept. Yes, is the only some particular values of energy are allowed for that particular wave. Then he applied this concept to try to explain the photoelectric effect. Then Albert Einstein, he described the energy in light waves as a quantum of energy. Then is that he called this quantum of energy, he called photons. Is we consider the light as a package of energy. It's something like, if this is the light, these are, we consider each of these is a quantum, and he called is like photons. Yes? This is the ray. Yes. Then each quantum has some particular value of energy. Then, because remember the energy he calculate in the experiment. They calculate in the experiment depend just the frequency. Then the Albert Einstein, he proposed this equation to calculate the energy for each quantum or each photon of energy in the ray light. This is the energy just for one photon. Yes, just for one photon. Then the light is made by billions of photons. Yes, but this is the energy just for one photon. Then he proposed this equation: the energy of the photon equals to the Max Planck constant multiplied by the frequency of the light. Yes. In this case, if we had red light, will be multiplied by the red light frequency. Then if we had blue light, then we had multiplied by the frequency of the blue light. And the mass and the Planck's constant equals to this value, which is really a small value. Then I want to explain in a simple way how Albert Einstein got this equation. Then what he did is he plotted the kinetic energy the Max Planck got in the experiment in the y-axis, and in x-axis he plotted the frequency. See? And what he got, the experimental data showed this behavior, which is a linear behavior. Then how we can get the equation that correlate the kinetic energy and the frequency? Just we need to calculate the slope of the line. And we need just to calculate the slope of the line. Then you see y, it's just he fit this data using the linear equation. Y is the kinetic energy, x is the frequency, and here is the y-intercept, is called the work function, is the minimum energy you need to apply to some material, for some metal, to electrons can escape from the material. Yes. Then we are interested more in this part. Yes. Then the x is the frequency, and the slope that he calculated was this value. And in honor to the Max Planck, he called the Planck's constant. Yes, in honor to the scientists conduct the experiment. Then you see here is the equation we use to calculate the energy of the photons. Yes, that part is we calculate is the equation, and it's just a linear equation. Yes, it's not any complicated equation. It's just where we correlate the kinetic energy with the frequency. Then in 1921, Albert Einstein he received this the Nobel Prize for physics, because he was able to explain the photoelectric effect. Yes, he got the mathematical relation that explain the photoelectric effect. In this example, we want to calculate what is the energy of a photon, of the red photon of light with a frequency of 10⁻14 Hertz. We want to calculate what is the energy. Remember, here is the energy for one photon of the red light if the frequency of the red light is 10⁻14. Then we know this is the equation we need to apply in this case. Yes, what we need to know is the Planck constant, which is this value, and is in your equation sheet, and the frequency, and we know the frequency. And let's write here the frequency is 4.00 10⁻⁷ Hertz. Then in this case we don't need to solve the equation, because we need to calculate the energy. And there is no problem with the units, because we know Hertz. Right here, Hertz is 1/second. Then we had the same units, second here and second here. Then we don't have problem. We don't need to convert units. And let's multiply the energy. Let's calculate the energy. Is 6.10⁻34. Let me write better this number. See. And 6.10⁻14. I have the wrong value here. Let me change this one. Minus 34 joules per second times the frequency, but the frequency is 4.0014. hertz is 1/second. Let's write here 1/second. Then let's check the units. This second cancel out with this seconds, and we had joules in the answer. And this is the unit we expected because it's energy. Now we multiply 6.63 times 4, and we had 26.5. Now for the power of 10, we have multiplication, then we need to add the exponents together, but one is negative, the other is positive. We need to subtract them. Well, negative 34 times 14 is negative 20 joules. If we want to write this one in scientific notation, then what we need to do is we need to move the decimal place one. We need to move the decimal point one place, and this is to the left. Then this we need to add 1. Yes, we need to add 1 to the power of 10. We move to the left, then we need to add 1 to the power of 10. Then we have 2.65 10 to the power minus 20 plus 1 will be minus 19 joules. And this is a small value. Yes, this is negative minus 19. But remember, this is the energy just for one quantum. And if you had the ray of red light, we had billions of quantums. Yes, then this is why if you add all these quantums, you will have the significant amount of energy. Yes. This is the quantum. This is the red light. Yes. Each of this, the energy for each quantum is 2.65 10 to the power minus 19 joules. But if you add billions of this amount of energy, then you will have significant significant energy. Then here, what is the present theory that which we can use to explain the nature of the life? And really, there is no one theory at this moment. What the scientists understand about the nature of the life is the particle model can explain how the light travel in the space, and can explain phenomena such as photoelectric effect. Yes, and this is how we can represent the particle model. Yes, this is the light as a string of photons. Yes, package of energy. Yes, this is packets of energy. But sometimes we need to apply the wave model to explain another phenomenon. Then the wave model explains how the light is emitted or absorbed by matter. Then the wave model can explain phenomena such as refraction, interference, diffraction, polarization, and I had to twice interference. And in this case, because the light is a wave, we can identify this wave if we know the speed of the wave, if we know the wavelength of the wave, and we know the frequency. And this is how we can represent the light as a wave. Then today the light is considered to have a dual nature. Sometimes acting as a wave, yes, but sometimes it's acting as a particle. But light never exhibits both properties at the same time. Then can be a wave, can be a particle, but no exhibit both properties at the same time. This is the current status about the nature of the light. Then the next thing I want to quickly review is the index refraction lab. And for index refraction lab, we will apply the Snell law. In this case, we will have in our experiment, which will be a virtual lab, you will use the one medium will be air, but the second medium is from unknown material. We don't know what kind of material. Then we want to find that material. Then because this medium will be air, then this is the equation we will use. And we will solve for the incident sine of the incident angle, and then we will get this one. Then what I want you to do, and I will, let's see if I can write here. I want you plot this. I want you plot. I explained this one in the procedure, but I want just to give idea what you had to do. Then let's see if I can graph here. Then I want you plot the sine of the incident angle in the y-axis. I want you plot the sine of the refraction angle, and then you will get something like that. It should be close to 0 here. And you can see this is like y equal mx. You can see the slope in this case corresponds to the index of refraction. This is the slope. And here you will have the y-intercept. Should be close to 0. Then what happens is the slope corresponds to the index of refraction of the unknown of the material we don't know. Then we want to find the index of refraction of that material to try to find this value using our book. The table appears in our book. Once you calculate the slope, you will know the index of refraction of that material. Using this information, this index of refraction, then I want you calculate the velocity, the speed of the light, yes, this value, the speed of the light in that medium, yes. Then in this, using this equation, you will solve for the speed of the light in that material. You know this one because you know the slope, you know the speed of the light in vacuum. Then you can calculate the speed of the light in that material, yes, in the material we use in our experiment. This is just, I want to show what you will find when you start the experiment. You will see something like that, and here you will have material 1 will be we will choose air. For material 2 is no glass. We will choose unknown material A, okay? Or I think mystery material. You say mystery material A. Then in the procedure I explain step by step. Also here there is an option you have to select here if you select the normal, then this will be show the normal line. Also you have to select this one. It will show the angles here. This is the source of light. You can choose any color you want. Another thing, we are not going to use the protractor to measure the angle because it's hard to read the exact value, and we need the exact value. But I want you had this one. You drag this one to here because I want you get close to some values, and I will show in the next slide. And here is the source of light. Yes, this is the source of light, and you can select any light, any color here. And let me show the next slide. Once you start the experiment, then you will have something like that. Then what I want you to do is using any light, yes, any light, we need to get the values of the angles, what angles we need to measure. Then these values, the program will when you choose the angles tool, will give the values, the exact values, and this is the angles I want you record in the table. I want you to record this angle, you see, and this is the incidence angle, this is the reflection angle, and this is the refraction angle. It corresponds to this one, but is this value. You see, here is hard to read here exact value, but here is 45. Then I want you to record this one. But this will be just to give you an idea, because we want about 10, 20, 30, 40, 50, 60, 70, 80 angle. Then this helps you to have some guide to choose that angles. But the values we will record in the table will be these values appear here. The other part you will read in the procedure, and then you use the procedure to conduct the experiments, and then write all the results in the lab sheet, complete the lab sheet, and submit online. I think this is all I had for today. Bye-bye.